Okay, so in today's video we're commencing a unit on gallery of graphs. So what we want to start to do is generalize our understanding of transformations that we've talked about relatively informally up to this point in terms of looking at graphs of parabolas, so quadratic functions, and graphs of cubic and quartic functions. So we're going to start from what we know about those functions, and actually the fact that these things also extend to our understanding of linear functions, though because a linear function is so much less complex we actually don't really need to think about it in these terms. But these transformations apply to all graph types. So what we want to start to do is see those general patterns that we've begun to see through a few specific graph types and start to generalize those so that we can then apply these transformations to other graph types. Throughout this topic we're going to be introducing new graph shapes, and we want to be able to start with what that basic graph shape is and then take our understanding of these transformations that's the same for all functions and apply it to those new graph shapes. So we want to get this sort of general understanding today before we move on. Right, so as I said, so far we've looked at linear, quadratic and cubic functions as well as a few quartics. So let's start off with one of the transformations that we've talked about. So when I talk about transformations, we're talking about dilations, reflections and translations. We want to start to formalize that language. Okay, so dilation rather than stretch or squash, we're dilating the graph by a certain factor and in a particular direction. We want to talk about reflections of the graph, so we're not flipping it, we're reflecting it in a line. So we'll just reflect graphs in the x-axis for now, and down the track we'll also talk about the fact we could reflect a graph in the y-axis. And then we're also going to look at translations. So again, not shifting or moving the graph, translating the graph by a certain amount in a certain direction. Okay. Alright, so let's start with dilation from the x-axis, which we've looked at in relation to our quadratics and our cubics. We technically have also looked at this in relation to linear graphs because it's about changing the gradient when you dilate the graph. So when the whole function is multiplied by a number, so when we have y equals x and then we multiply that by 2, so y equals 2 times x. We have y equals x squared, we multiply that by 2, and so we get y equals 2 times x squared. We have y equals x cubed, we multiply that by 2, and so we get y equals 2 times x cubed. Okay. All three of these things, the same thing is happening to the graph. Okay. And what's actually happening is that the graph is being stretched away from the x-axis by a factor of 2. It's being dilated from the x-axis by a factor of 2. And what that means is the y-coordinate of every point on this graph is being doubled. So for example, let's have a look at the parabola here. This point here that I've started with here, that's 1, 1. We doubled the y-coordinate and it's now up here at 1, 2. This point here is 2, 4. We double the y-coordinate and it's now up here at 2, 8. This point here is 3, 9. We double the y-coordinate and that point is now up here at 3, 18. Okay, so 2 times x squared is the graph of x squared dilated from the x-axis by a factor of 2. Every y value is doubled. It's the same with the linear graph. Y equals x goes through 1, 1. Y equals 2x goes through 1, 2. We're doubling the y values. Okay, you can check the numbers there. Same down here. When x equals negative 2, y equals negative 2 on the original graph, y equals x, we double the y value and we're now down here at negative 2, negative 4. Okay, doubling the y value, etc., etc. Okay, so the cubic is the same. Goes through 1, 1, we double the y value, 2 times x cubed goes through 1, 2. It goes through 2, 8. We double the y value, 2 times x cubed goes through 2, 16. So we're stretching, dilating away from the x-axis by a factor of 2, and what that's doing to every point on the graph is it's doubling its y-coordinate. So it's the same for y equals x, it's the same for y equals x squared, it's the same for y equals x cubed, it's the same for y equals f of x. If we draw the graph of y equals 2 times f of x, we have taken y equals f of x and we have doubled all the y-coordinates. We have stretched the graph, dilated the graph away from the x-axis by a factor of 2. Okay. Alright, reflecting in the x-axis, when the whole function is multiplied by negative 1. the graph is reflected in the x-axis. And what this means in terms of what's happening to all the points is that the y-coordinate of each point has been multiplied by -1. So for example, in the first graph here, we have y equals x. Multiplying that by -1, we get y equals -x. And what we're seeing happen here is each point, we're multiplying the y value by -1, and it is now on the other side of the x-axis. When we multiply the y value by -1, the impact of that is to reflect the graph in the x-axis. Same with the parabola. Y equals x squared versus y equals -x squared. So the whole function multiplied by -1, remembering that -x squared means -1 times x squared. It's not the same as -x all squared. Okay. And so again, the y values have all been multiplied by -1. And so the effect of that is to reflect the graph in the x-axis. 1, 1 has gone to 1, -1. 2, 4 has gone to 2, -4. 3, 9 has gone to 3, -9. 4, 16 has gone to 4, -16. Same over this side. -2, 4 has gone to -2, -4. -3, 9 has gone to -3, -9. And so we've reflected the graph in the x-axis. Same with the cubic. The cubic goes through 1, 1, y equals x cubed. Multiplying that by -1 means that the y value becomes negative, and so it now goes through the point 1, -1. 2, 8 becomes 2, -8. 3, 27 would be down here at 3, -27. Okay. Same here, 1, -1, multiplying the y coordinate by -1 goes to 1, 1. 2, -8 goes to 2, +8. And we get this mirror image happening to our graph, okay, reflected in the x-axis. And again, we can generalize that to all functions. So y equals x, y equals -x is y equals x reflected in the y-axis. Y equals -x squared is y equals x squared reflected in the x-axis. Y equals -x cubed is y equals x cubed reflected in the x-axis. Y equals f of x, when we multiply it by -1 and get y equals -f of x, it is a result. It causes a reflection in the x-axis. Okay, so the graph is mirrored over the x-axis. And then we can talk about translations up and down to start with. So when we add a number or subtract a number from the whole function, okay, x plus 5, x squared plus 5, x cubed plus 5, x to the 4 plus 5, x to the 27 plus 5, square root of x plus 5, okay? The impact is going to be the same. Adding or subtracting is translating up or down. When we add 5, we go up by 5. We've already had a look at these transformations in specific graphs. The next one's the one we need to be a bit careful of. And so we can generalize that. So when we go up by 5, translate up by 5, we're not multiplying every coordinate by the same thing, we're adding. We're adding on to the y coordinates of every point, okay? Adding 5 onto the y coordinate of every point moves the whole graph up by the same amount. Pick any point, add 5 onto its y coordinate, you get the new point on the graph. Add 5 onto the y value, add 5 onto the y value, add 5, add 5. Okay, in the case of the parabola, it sort of looks like it's changing the shape of it, but it's actually not. It's just because we're looking at it in a different window, okay? The whole graph has been translated up by 5. Same with the cubic. It looks like a slightly different shape, but it's not. Take that point, move it up by 5. Take that point, move it up by 5. Take that point, move it up by 5. Up 5, up 5. We end up in the same place, okay? So take the whole, adding 5 onto all the y values is going to translate the graph up by 5 units, okay? I'm just perhaps going to flip over to the graphs just to have a quick look, because we've talked about this before, but this is the one we need to be a bit careful of. Let me just open up my CAS here. So at the moment, now this is a slightly more complicated version because I want to come back and talk about this, but I've got everything happening here all at once. So I've got a black graph which you actually can't see at the moment because it's underneath the red graph, because they're actually currently the same thing, which is just y equals f of x. Now in this particular example, let me just go over to the other screen, f of x is x squared, okay? So y equals f of x, which is y equals x squared, and then we've got y equals a times f of x minus h plus k, okay? So at the moment a is 1, so that's the dilation and reflection, so there's no dilation or reflection happening. H is 0, That's the horizontal translation, which we're about to talk about, and k is 0. That's the vertical translation, which we're about to talk about. So let's just have a play around with these while we know. So we know a, when we increase a, that's about dilating away from the x-axis. If we made a fraction, it's going to mean that the graph gets wider and flatter. We're still dilating from the x-axis, but if you dilate from the x-axis by a factor of 0.2, as we are currently, you multiply all the y values by 0.2, they become smaller, and therefore the graph becomes wider and flatter and closer to the x-axis. If we were to keep going and making a smaller and make it negative, we also get that reflection. So at the moment here, let's have a look at this one, a is equal to negative 2. So there are two things happening there, reflection in the x-axis and dilation from the x-axis by a factor of 2. Okay, so we've talked about a, dilation from the x-axis, multiplying the y value. We've talked about k. We make k bigger, my graph goes up. We make k smaller, my graph goes down. So I know it's a little small to see here, but you can see k is negative 3 at the moment. The graph has been translated down by 3. Now I want to be a bit careful here, and I've set this up in a particular way. We want to look at the translation left or right, and this requires your function notation to be a bit better than the other two, and we'll talk more about function notation over the course of this topic and the next topic. So we're looking at adding or subtracting inside the function f of x minus h. Now I've set this up in a particular way. I've written it as x minus h. So as I make h bigger, so here h is 1. This is the equation f of x minus 1. And this is the quadratic, so this is x minus 1 all squared. This is x minus 2 all squared. This is x minus 3 all squared. So when it's a minus, the graph actually goes to the right. If I make h a negative value, so here h is equal to negative 1, subbing that into this equation, that would give me f of x minus minus 1. So this is f of x plus 1. In the case of the quadratic, this is x plus 1 all squared. This is x plus 2 all squared. This is x plus 3 all squared. So remember, these horizontal translations, they look backwards in the equation. We're going to go into a lot more algebraic detail about that next year. For now, we want to observe the patterns and come to understand what's happening, okay? So we need to understand, and it's to do with the fact that the number is inside the function. And we'll see when we, a bit down the track in a few lessons, we'll introduce 2 more transformations, and we'll also see there's a slightly backwards impact with one of those in particular. So in this particular example, we've got our 3 functions, y equals x squared, y equals x cubed, and this time we've got y equals x minus 3, which means it has gone to the right by 3. Now, in the case of the linear graph, and this is why we don't talk much about translations with linear graphs, because there's not enough going on, y equals x minus 3, putting the negative 3 inside the function, is exactly the same as x minus 3. So actually in this case, it's the same as having gone down by 3. So that's why we don't really talk about translating left and right much with the linear graph. However, the other graph shapes, it's an important distinction. X minus 3 all squared is a different thing to x squared minus 3, and that's the distinction, okay? X squared minus 3 is down 3. X minus 3 all squared is right 3. Okay, it's really important you see the difference in what's happening there. Okay, so when we're translating left and right, we're adding onto the x coordinate. So to the right by 3, we've added 3 to all the x coordinates. The whole graph translates to the right by 3. Similarly with the cubic, okay, again the distinction between this is an x cubed minus 3, which would be down 3. This is x minus 3 all cubed, which is to the right by 3. So again, taking every point, adding 3 onto its x coordinate, we get to the new point, okay? And so we get our new graph translated to the right by 3. Again, we can generalize that, taking y equals f of x, any function, doesn't have to be x squared, doesn't have to be x cubed, any function, and making it f of x minus 3, so replacing the x in the function with x minus 3, results in the graph being translated to the right by 3 units. As I said, in time we'll also need to add in 2 extra transformations, and we'll talk about those when we introduce a graph shape where they become important. Reflections in the y-axis and dilations from the y-axis. They're the two that are missing in the current set, okay, but for now we're not going to worry about those. Alright, so I just want to go back to the graph for a minute, and I want to generalize this a bit. So let's put this back to 0 so they're the same function. Okay, so now I'm going to change the function definition. I just need to get my CAS open so I can do that. Alright, let me make it a function that we don't know anything about. Let's make it, 1 over square root of x. Okay, and this isn't a function shape we're going to become particularly familiar with, certainly not this year anyway. So I just want to introduce something that you don't know what it looks like. In fact, I might make it that plus x. Let's see what that looks like. Okay, so now if I go, sorry, I need to go this way. So now there's the graph. Okay, this is this new graph shape. Y equals the square root of x plus x, 1 over the square root of x plus x. Okay, not asking you to draw that graph. I'm just going to give you a general shape that is not about you coming up with the equation. Okay, it's about you understanding the impact of A, H, and K. So again, let's isolate each one. So I know that if I were to make A 2, it would take every one of these points on the graph, multiply the y values by 2, so it's stretched further away from the x-axis, okay? And there it is there. Perhaps if I adjust my y value here. Sorry, let me make that maybe 10 so we can see a bit higher up here. Okay, so we have stretched this graph. We've dilated it by a factor of 2 from the x-axis. You can look at each of those points there. You can take any point on that graph, double its y value. Any point on the black graph, double its y value, and you get the equivalent point on the red graph. Again, we can look at making a fraction. So this is where a is 0.4, for example. Okay, so every y value has been multiplied by 0.4. It's a dilation from the x-axis by a factor of 0.4, and that means that if we're multiplying all those y values by 0.4, they're getting smaller, and so the graph is getting squashed, but it's still a dilation. It's just the fact that the dilation factor is less than 1 makes it a squash rather than a stretch. Okay, we continue to make a smaller so that it's negative. So there's let me make a negative 1. There's a equals negative 1. So it is the mirror image if we make this negative 10 as well, so we can see what's happening here. Okay, it's the graph reflected in the x-axis. Alright, if I put a back to being 1, now we look at k. Okay, k, so if we make k 1, we translate the graph up 1. K is 2.5, we've translated the graph up by 2.5. K is 4.5, we've translated the graph up by 4.5. We can translate the graph down by 1, down by 2, down by 3.5, translating it down by 5. Okay, literally just subtracting 5 from all the y values. It's the same shape, translated down by 5. So this would be 1 on root x plus x minus 5 is the equation we're dealing with here. So take the whole function, subtract 5 from that. Alright, then we get into the translations left or right. So this is x, f of x minus h, so translating left and right. Again, x minus 2 goes to the right by 2, x minus 4 goes to the right by 4. X minus minus 1, so x plus 1 is to the left by 1. X minus minus 2, x plus 2, f of x plus 2, sorry, is to the left by 2. Okay, so we want to start to get this sense of seeing these transformations more generally rather than applied to specific functions. So once we can generalize them, then we're really going to be formidable in terms of how we draw graphs. We can then introduce a new graph shape and take our understanding of transformations and apply that to that same graph shape. Okay, so let's go back over to our notes here. So let's have a look at some examples. In each of the following, y equals f of x is shown. On the same axis, we want to sketch a different graph. Now, this question isn't about coming up with the rule for y equals f of x, although we could technically. It's a quartic function and we've got lots of information about it. However, it's not about that. It's about looking at the picture you've got of f of x and thinking about how is 3 times f of x different from that. Okay, so 3 times f of x, okay, I might just change my pen so it's a bit different from that red colour we've already got with the graphs. So 3 times f of x is a dilation by a factor of 3 from the x-axis. all of the y coordinates are being tripled. So this point at 1, 4 is going to go to 1, 12. Okay? This point at 3, 0, when we triple its y coordinate, 3 times 0 is still 0. So it stays where it is. Same with this other x-intercept. 0, 9 on 4, okay, tripling the y coordinate is going to be 27 on 4. Now 27 on 4 is 6 3/4, so that's going to be sort of about there. Okay. This one was 112 up here. Sorry, it's a bit crowded. And you could take another point. There's a few other points we can see here. This point looks like it's roughly at 4, 6. So tripling that would go to 4, 18. Okay, way off the charts. So you get a sense of what's happening. Okay. Again, you could take any point. The y value there, the y value here, for example, is 1. So tripling that, it's going to go through this point here. Okay. Y value here is 1. Tripling that, it's going to go through this point here. Okay. So essentially, we've got our graph. Y value is 1 here, so we triple that. It's going to go through here. So mark yourself a few points on so you can get a sense of the shape. It's going to be taller and thinner because it has been stretched away from the x-axis by a factor of 3. Okay, so that's essentially the graph of 3 times f of x. F of x dilated from the x-axis by a factor of 3. Sketching the graph of negative f of x. So sticking a negative in front is going to be reflecting that graph. So we're going to draw a reflection in the x-axis. All the y coordinates get multiplied by -1. So 1, 4 goes to 1, -4. 3, 0, multiplying its y coordinate by -1, it's going to still stay at 3, 0. Same with -1, 0. Okay. Pick some other points on your graph. So 0, 9 on 4, which is just a bit more than 2, 2 1/4, goes to 0, -9 on 4. Okay. That'd be a nice symmetric point over there. You could pick another point, this point somewhere around here. It's about 6 and a bit, -2, 6 and a bit, goes to -2, -6 and a bit. Okay, same with this one over here. Looks like 4, might be 4, 6, might be 4, 6 and a bit. It's a bit hard to tell from the scale, but just give you a rough sense of what's going on. So you're looking at, you can take this point here on the end here and make sure that that's reflected in the y-axis as well. Okay, and so we essentially get. Sorry, our quartic graph, same shape, just upside down. But we can be quite technical about that in terms of actually mirroring a selection of points so that we're getting a precise graph. So this is now at 1, -4, this turning point. This y-intercept is now at 0, -9 on 4. Okay, your x-intercepts are still at -1, 0 and 3, 0. Okay, sketching the graph of y equals -2 times f of x. So the negative is going to reflect it in the x-axis. The 2 is going to dilate by a factor of 2 from the x-axis. So we're going to multiply the y values by -1 and also double the y values. So 1, 4 goes to 1, -4 when we reflect it in the y-axis, sorry, reflect in the x-axis, and then we're also dilating, so it goes actually to 1, -8. 3, 0, reflect in the x-axis and dilate by 2, stays here. Reflect in the x-axis and dilate by 2, -1, 0 stays there as well. 0, 9 on 4 goes to 0, -9 on 4, and then we double that, so that's going to be 0, -9 on 2. Okay, 4.5, sorry. And again, you could take another point, reflect it in the x-axis, and then also double it. It's going to end up double its y value, I should say, sorry. It's going to end up further down here. Alright, so we've essentially got a steeper, sorry, try that again. A steeper and upside down graph as a result of the dilation and the reflection. Mark in whatever points you can. This is 0, -9 on 2. So actually transforming those 4 points that you've been given on the graph. Sketch the graph of f of x minus 2. Okay, so adding or subtracting onto the whole function is when we go up or down. So this is a translation down by 2. So taking each point and translating it down by 2, 1, 4 goes to 1, 2. 3, 0 goes to 3, negative 2. Negative 1, 0 goes to negative 1, negative 2. 0, 9 on 4, which is 2 1/4, goes down to 0, 1/4. Okay. And you could take a few other points and move them down by 2, and move them down by 2. Okay. And essentially you're going to have a graph that does this. Okay, so marking in the points you can, 3, negative 2, negative 1, negative 2, 1, 2, and this point here was 0, 1/4. Sketch the graph of f of x minus 2. So subtracting the 2 inside the function is going to the right by 2. Okay, so again, moving your points to the right by 2, 3, 0 now goes to 5, 0. Negative 1, 0 goes to positive 1, 0. 1, 4 goes to 3, 4. 0, 9 on 4 goes to 2, 9 on 4. Okay. And we can essentially draw in our graph. You might like to move another couple of points over just to give you a rough shape. Sorry. Make sure it goes in a bit higher than that. Yep. Okay, so it is the same graph translated to the right by 2. And then we can start to combine all those things together. So we've got dilation, we've got dilation by 2 from the x-axis. We're going plus 1, so that's left 1, and plus 3 is up 3. So we're going to take each point, we're going to dilate it by 2 from the x-axis, so that is to double its y-coordinate. So 1, 4 goes to 1, 8. Then we're going to move it to the left by 1, it goes to 0, 8, and then we're going to move it up by 3. It now goes to 0, 11. Okay, do that for each point. Dilate it by 2 from the x-axis, multiplying the y value by 2, doesn't change. Left by 1 and up by 3, it now goes here to 2, 3. Again, the dilation doesn't change the y value at the point negative 1, 0. Moving it to the left by 1 and up by 3 means we're at negative 2, 3. 0, 9 on 4. Dilation by 2 from the x-axis makes it 0, 9 on 2. And then we're going to move it to the left by 1. 9 on 2 is 4.5. Left by 1 and up by 3. So it goes up to 7.5. Okay, and again, you might take a few extra points, but you're essentially going to have a graph that turns here at negative 2, 3. Back up to that point. Now we worked out what that point was. That was negative 1, 7.5, or 15 on 2. We can combine together those transformations. We'll keep the combinations relatively simple this year, but next year we need to deal with quite complex combinations of transformations. Okay, last example here, we want to describe the transformations that map y equals g of x to y equals 5 times g of x. So we talk about mapping. We create a new graph using transformations. The new graph is a result of having mapped the old graph to a new set of points. Okay. So describe the transformations that map y equals g of x to y equals 5 times g of x. So the 5, what impact is that having? We want to use the right language, so we want to use the word dilation, reflection, or translation. This is a dilation by a factor of 5 from the x-axis. It's not enough just to say that it's a dilation, okay? You're telling me, okay, it's been stretched. That's not enough for me to draw it. How much am I stretching it by, and in which direction am I stretching it? I'm stretching it by a factor of 5 away from the x-axis. Okay. There are other ways to describe the direction. We'll talk more about that next year. I think for this year, let's just stick with from the x-axis. Okay, and thinking about the fact that that changes the y coordinates. Okay. Describe the transformation or transformations that map y equals g of x to y equals g of x plus 8. So that plus 8 is inside the function. That's left or right, okay? This is, we have to use the correct words again, so translation, 8 units to the left with plus 8. G of x minus 3. So the additional subtraction outside of the function, okay? So this is the difference between, if this function was x squared, this would be x plus 8 all squared. That's left by 8. This would be x squared minus 3, okay? So completely different what's happening here. So this is, again, a translation, and it's by 3 units down because of the minus. Okay, part D, we've got negative half. So we've got two things happening here, the negative and the half. So the negative is reflection in the x-axis. So again, you need to use the word reflection, not flip. Sorry, let me get rid of that keyboard for you. We need to use the word reflection, and in what line are we reflecting? So we don't reflect on an axis. Okay, we don't reflect by an axis. We could reflect through an axis, but in terms of correct language, let's talk about reflecting in the x-axis, in the same way that you look at your reflection in a mirror, not on a mirror. So reflection in the x-axis, and then we also have dilation by factor 1/2 from the x-axis. Okay, so again, we can't dilate in an axis. Okay, you wouldn't stretch in a line. You stretch away from a line, or in the direction of a line, or parallel to a line. Okay, we'll stick with away from a line for now. Okay, part E, again, we've got two things going on. We've got the 3 out the front, and we've got the minus 2 inside. Okay, so the 3 is reflection. Sorry. Not concentrating. The 3 is dilation. I was reading the example above. Dilation by factor 3 from the x-axis. Okay, so we're tripling all the y coordinates. And then the minus 2 inside the function is translation to the right by 2 units. Alright, and then part F, again, we've got two things happening here. We've got the negative out the front, and then we've got the plus 6 at the end. Okay, so the negative is reflection in the x-axis, and the plus 6 is translation up by 6 units. Now, the order is really important. The only one where the order is important is in this one. Okay, I'm going to try not to worry too much about confusing you with the order. I'm going to, in year 11, next year again, that's a whole other added level of complication. It's not correct if you write those out of order. So I'm going to be giving you the transformations in a way that you should always be able to give the dilation. So the format I'm talking about at the moment, it's always going to be the dilation and or reflections that happen first, and then after that, the translations, okay? We're going to always make sure we reformat things in a way that enables us to give them in that order every time. Dilations and then reflections, and then the translations after that, okay? All right, last one here. Sorry, I skipped ahead before, so get rid of that. Write down the new equation if the following transformations are applied to the graph with the equation y equals square root of x. Okay, so we have f of x equals square root of x. Dilation by 7 from the x-axis. So we know that this is when f of x becomes 7 times f of x. So for this particular function, that's going to mean y equals 7 times f of x, which is root x. Translation up by 1 unit. So that is when f of x becomes f of x plus 1, okay, up outside the function. And so for this particular function, if f of x is square root of x, that's going to mean y equals square root of x plus 1. Reflection in the x-axis, okay, so that is when f of x becomes negative f of x. So if f of x is square root of x, we're sticking a negative in front of that, the negative of f of x, the negative of square root of x. And then translation to the right by 3 is when f of x becomes f of, now remember it's x minus 3, not x plus 3 when we go to the right. So this time we're replacing the x part of the function with x minus 3. So this is going to become y equals the square root of, instead of square root of x, square root of x minus 3. So if we're translating left or right, the addition or subtraction goes in underneath the square root, whereas up and down in part B, the addition or subtraction goes outside of the square root. Okay, so it's a worksheet for you to work through today, having a play around with these different transformations and generalizing your understanding of the transformations to be able to extend them to graphs other than parabolas and cubics and a little bit of quartics.